Okay, so I've given you an example about localized deformation on a macroscopic scale caused by variations in texture. Basically, a seam welded tube, basically that was where it's welded. Where the weld structure is isotropic, will tend to fail in the weld simply because of the biaxial stress conditions, but that doesn't happen for a tensile specimen. I'm going to move on now to another form of localized shear, not the macroscopic one, but the microscopic one. And this is one that probably you're all mostly familiar with, which is the shear bands or channeling that are observed in irradiated zircaloys in particular, but also in the same phenomenon occurs in steel. So when I talk about steels and zircaloy here, I'll be doing it interchangeably, unless of course I start talking about helium bubbles, which is only in the steels. So when it comes to localized shear on the microscopic scale, in fact, there's quite a bit of ambiguity about how people describe it. There is such a thing known as channeling, which is reasonably well, it's very well understood, in fact. And that gets confounded often with what is planar shear, which is just simple dislocation slip on a given plane. And that then leads into confusion about what could contribute to a phenomenon known as pileup, which is basically an amplification of the stress at the head of a slip band where it intersects a boundary or some other barrier. So one of the things that's quite apart from the confusion between what is channeling and what is planar shear, there's confusion then with identification of channels in the TEM and basically the interpretation of images in terms of channeling when potentially they should really be interpreted as twins. And that's just a question of doing more detailed TEM analysis than some people might conduct. So let's get into it. We'll start by giving some examples of what do we mean by channeling. Well, on a, if I was to summarize, not just making this up now, channeling happens in irradiated materials, and it happens because for whatever reason, the deformation, dislocation slip, becomes localized, occurs at a given point, and the dislocations run through the material, sweep through the material in layers, which are basically parallel with the slip plane, and sweep out the dislocations. In doing so, they sweep out and they create these dislocation loop free zones. And as you can well imagine, if you've got some radiation damage here and none here, this is a softer zone compared to the matrix. So in this case, this is zircaloy 2 irradiated at 60 degrees centigrade. You've got a lot of channels running into a boundary here. We'll talk about the interaction of boundaries, of channels with boundaries, but just make a note that there's nothing happening at the boundary. There's no cracks forming or anything like that. But also note that the channels are not planar necessarily, and they're varying in width, and basically there's a lot of complexity there when it comes to cross slip and moving on to different on a more macroscopic or less microscopic scale, a non-planar kind of clearing or channel morphology. So how is this manifested in the in a bulk specimen. Well, when you get channeling, what you get is a load drop. So if you have a test which is strain driven, when a channel is first formed, there's basically it becomes easier to deform, and there's a load drop, as you see here. And in this is a stress strain curve. You see the irradiated, the non-irradiated part here, and then this is the irradiated part. So this, what irradiation does, it increases the yield strength and the ultimate tensile strength. And then when you deform, when you eventually start to form these channels, you get a load drop, and if you follow the stress strain curve along, at some point, often you get a second load drop, and that would be because the secondary slip systems that start to become initiated. And that's demonstrated here in another example. This is from some French work with Frigenes and Lemagnon. This is from some work from the US, Bailey and company. And basically, in this case, I think they're both roughly about the same temperature, radiation temperature, but they're tested at room temperature. In this case, you've got this nice, beautiful load drop here corresponding with a channel formation, and then a second load drop when you get this second slip system kicking in. As you might expect, as you get closer to the failure point, the necking, the broader necking of the sample increases, and the stress in the thinned down section of the gauge increases significantly, and eventually, and with all the strain that's involved, maybe hundreds of percent strain, you eventually get failure. So how does this load drop phenomenon, it's pretty common in all metals, how does it compare between austenitic steels and ferritic steels? So here's ferritic steels, austenitic steels, and zircaloy. You can see the effective irradiation going from an unirradiated material, in this case, to the irradiated material, is that in the austenitic steel and the zircaloy, you get this load drop, and that's related to the channeling. Now, in the ferritics, it's not so much of a load drop, because even in the unirradiated state, you have this region of Luder's band formation, which is typically from twinning, I think, or strain aging, or some. Well, it can't be strain aging in this case. It's a room temperature test, but I'm not going to talk about that because we're not going to talk about ferritics. But the reason this is on here is just to illustrate how irradiation, even low dose irradiation, severely embrittles the material. So although it increases the hardness immensely, there's a very severe embrittlement that's associated with that. And that's understandable. I mean, the more applied stress that you have, the more chance you have of getting the amplification effect from a pileup, which I'm going to talk about in a few slides. So let's move on. And what is the channeling? This is what we're interested in right now. So channeling is this phenomenon where the gliding dislocations sweep through the material and pick up the prismatic dislocation loops. But what that means is that you might start off with a slip band or a slip plane where all the dislocations are in one plane, but as they sweep up and accommodate the loops, their slip plane will vary, and the channel height, if you like, will broaden. So we're looking, if you imagine this, we're looking parallel with the slip plane in the direction of the shear, a distance along from the source where a dislocation slip band, yeah, call it slip band. I'm going to call it. Band is a misnomer, but a dislocation slip system is operating, and as it moves further, the volume of material over which the dislocations are active expands, much like a twin. But the shear is in this direction, and the strain is always in the plane of the paper here. Sorry, perpendicular to the plane of the paper of the slide in this particular case. So what are we talking about? So basically, a dislocation will be moving through a crystal. It'll come up against a prismatic loop. It'll incorporate the loop. I mean, this is a very, very simple scenario here, and carry on. In doing so, this portion of the dislocation has climbed compared to this. So, but the dislocation being an edge dislocation in this case, it only works for edge dislocations, although I think there can be some helical climb interactions, but I'm not sure how that necessarily sweeps up the loops for screw dislocations. Perhaps the screw dislocations allow the loop to move out of the channel easier. I don't know. The observation is that you get this clearing. The mechanism, which seems to be widely accepted, is just simply incorporation of the dislocation into the gliding dislocation. And what we end up with then is this broadening of the plane over which the dislocation interacts with the material. Here's an example from some dislocation dynamic simulations. Unfortunately, don't have the simulation. I asked this guy Tariq if he had a video, and he said he doesn't. So he gave me this and a presentation of his, not a presentation, but a reprint. And it just basically shows in a simulation exactly as what we had showed you there in that channel broadening, if you like, that you get dislocations traveling through the material and sweeping up the loops. Okay, so I mentioned how normally shear dislocation slip is on one plane. Now it can be an edge dislocation like this, or it can be a screw dislocation. It doesn't really matter. The thing to pay attention to is that the deformation is on one plane. So we've got a planar shear. So I think where the ambiguity comes in, and this is where I really want to emphasize this now, in calling these things slip bands, is typically people will observe dislocation slipping on a slip plane in a TEM foil, which is really a slice through the material. So you're taking a thin slice through the material, and then when you look down on the slip plane, what you actually see are these segments of the dislocation having cut off the rest of it. And this then gets called a slip band. I'm not sure that that's exactly the right terminology, but we'll call it a slip band for the sake of argument, because even though it's not particularly correct. But the implication here, and I think this is where sometimes I think some people get mixed up with this. It appears like it has a finite width, but it really isn't. It's just that it's basically an artifact. If you think of it in those terms, it's human produced. It's an artifact of the preparation and how one images the material. So dislocation slip appears as a narrow channel in TEM because we're looking at a projection. And so channel, that's the right way to describe it. Here's another couple of schematics just to show how one would view a slice through a slip plane and how it would appear in the microscope. And if you really wanted to verify that you have slip on one plane, you'd have to tilt the slip plane to the edge-on configuration, in which case you'd just see little lines like this. Oh, I've got 2 slides in here somewhere. Oh, and again, the issue here is we need to distinguish about what is a slip band and what is a channel, and the whole issue of planar slip. So this brings us on to pileup, and pileup is a mechanism where the stress at the head of a dislocation, a series of dislocations, if that are following one another, when they hit a barrier and the lead dislocation is held up, there can be a situation where you can get some amplification of the stress because of the way that the dislocations interact. And this is just from a paper by a guy called Roman Voskoboynikov, and it just shows that if you have lots of dislocations and you have a very large difference between the applied stress and the stress necessary to move the dislocation, then you can get a significant amount of amplification. I'm not going to go through this, but ultimately there have been lots of studies about it. But what you need to pay attention to is that by considering situations such as this, where you have dislocations which are emitted from a source, it could be screw or edge dislocations, and then these dislocations move along a slip plane and then come into a block, a barrier. The stress at this point, the shear stress in this particular case, the stress at this point can increase significantly, and the shear stress of the lock is given by this expression, where n is the number of dislocations in the slip band, and the external shear stress is given by sigma x, and sigma I is the lattice friction stress. So this concept was first conceptualized by Alan Cottrell and later formalized by Eshelby. Eshelby and company had a very nice, elegant study to show that these dislocations, where their equilibrium position, if you like, depending on the applied stress and the number of dislocations, can be reduced to a polynomial, and where the dislocations are their positions, where basically zero or stable minimum in the energies, the minima are roots of the polynomial. It's kind of neat. Okay, so where does this take us? Well, you can either think about that increased stress, and if you take it to an extreme, many years ago, the likes of Stroh, when I was at school, it was Stroh, I guess because he was English, but other people quote this other guy, Zener. It seems like they both invented or discovered or conceptualized the same thing at the same time, so it's kind of difficult to know who was the originator of the thought process. Either way, it's kind of a very esoteric. It's certainly a concept, and because I'm not sure the proof has ever been established fully. So the idea is that if you have enough dislocations in the lock, in the slip band and against a lock, and the applied stress is sufficiently high that let's say it's 10 times the lattice friction stress, it is possible then to force dislocations together and create, on a microscopic scale, a crack. But even for two dislocations, the applied stress at this point has to be extremely high. 20 gigapascals is roughly what one would expect for two edge dislocations. So in getting to this amplification situation at a lock, there's been a lot of study about channeling, because I kind of think in the mistaken belief that channeling somehow gives you is an indication of this amplification happening. Well, as I explained earlier, channeling itself is a bulk shear. In effect, it becomes more like a twin when it advances, and the dislocations are not all lined up one behind the other like a train, and so the channel itself, when it interacts with a barrier, cannot generate the kind of stresses that Cottrell and Eshelby conceived of, and also Stroh conceived of, and what you have to then get into is a kind of an argument or hand-waving discussion or hypothesis that once you've got the channel created, that opens up the material, softer material, and would allow more slip, and then you could create a slip band. But again, just so that you're aware of this, that is something that it's an extra step that one has to hypothesize that may or may not apply. It's okay to be hypothetical about all of these things, but sometimes it's establishing the proof is not so easy. So guys who did a lot of work on strain localization, and actually T.S. Bjorn here, he wrote a very nice paper on it entitled Localization of Strain, and they've done a lot of characterization of deformed stainless steels. Ken Farrell, I guess, is he still going? I don't know, but anyway, Ken Farrell is somebody I know from the UK, and he was very much a part of the effort that these guys went into over many years, producing a lot of work, a lot of very good work, TEM in particular, looking at strain localization in connection with deformation mode maps. And I'll show you one. Oh, I think I showed you earlier. So by and large, if you read any of the papers, they'll often say, well, we see a mix of channels and twins. So just making it very clear to everybody that you have to be careful that you don't mistake twins from channels. But you can often, I think easily, but you can tell when you have a twin because simply from the contrast, because the channel itself should not change the diffraction contrast. There'll be a contrast difference simply because of there are fewer loops in the channel, but the actual, if you look at the actual matrix and the scattering of the electrons, that should not change. Oh, sorry, it should not, it will not change in the channel, but it will for a twin. So these guys did some very nice work as well, just to show, just if anybody's curious, because often people focus on channels and they ignore the fact that when you deform, when you produce a stainless steel sample, when it's mechanically core worked, for instance, or deformed in some way on the right conditions, you produce all kinds of things. It becomes a very complicated microstructure, and they broke it down here into the type of stuff you generate depending on the strain. At low strains, dislocations. At higher strains, in this case, this is for 3 or 4 stainless steel, epsilon martensite, as well as dislocations. And then at very high strain, well, 20% strain, they greater than a certain stress here, 600 megapascals, and that corresponds to a number that TSBN came up with. It basically, at around about 600 megapascals, a twin formation can occur. And then they go on and you get other stuff, including even the alpha prime martensite, except I'm not sure they mean the BCT form. I think they probably mean the BCC form of martensite. Okay, so twinning is pretty common. We should understand it a little bit better. Now for zirconium, zirconium is an interesting material in that there are lots of opportunities for twinning. And just as there are lots of opportunities for different slip systems, because you have this a range of planes which have a similar atom packing density, and so the variability, if you like, in the shear stress, the pile stress needed to operate slip systems on these different planes, there's not a big spread, and you can, in fact, depending on the stress state, you can generate all kinds of dislocations. Well, you can generate C component dislocations as well as A type dislocations on different planes. The planes inclined to the basal plane, the C plus A type dislocations. On this thing that I stole off the internet, it talks about a C dislocation, but that wouldn't be a slip dislocation. It's not possible to get C slip. But it is possible to get A slip both on the basal plane and the prism plane, prism 1 plane. Oh, it's also possible to get A slip on this 1/1 first order pyramidal plane. So if I had my, when I give this presentation live, I'll have some ball models and I'll be able to demonstrate simply how slip operates on all these different planes. The interesting thing about zirconium is even though the basal plane is the most close packed plane and is indistinguishable from the FCC 111 plane in how the atoms are packed on a single plane, that's not a twinning plane. And that's just simply a geometrical consequence of the ABA stacking in the hexagonals compared to ABC stacking. And what that means is that a twin, which involves the shear of a partial dislocation on each successive plane in a given volume, that really is what a twin is. It's not possible on the basal plane, but martensite transformations are. So you can shear every second plane in the same direction. And again, I can demonstrate that when I have my ball models. Okay, so lots of possible options for twins in the hexagonal system. But in terms of channeling, a lot of the ambiguity comes up when it comes about when you have twins in the FCC system. FCC, face-centered cubic system, austenitic alloys. So there's only one twin to consider, and that's one that shares a common plane with the normal slip direction, the dislocation slip, the A/2 110 slip. But twinning itself is again, depending on what the what the situation is, and I'll talk a bit more about that. Twinning can sometimes occur in preference to dislocation slip, but the difference between them is that one is this planar shear, and the other one is a bulk shear. Planar shear, bulk shear. What the twin does is it actually makes life very complicated, because it's actually you're talking about a mirror, taking a mirror image of the atomic planes in the Barron 1-0 plane, which is perpendicular, not perpendicular to, but the mirror image, excuse me, the mirror is perpendicular to, the image plane, the mirror image plane is the 1-1-1 plane. And this is, you can see this if you look down the Barron 1-0 direction, and you can see the effect of the twin shear. And the twin shear occurs over 3 planes, 1, 2, 3, and by the time you've moved from there to there, the displacement you've taken is a half 1-1-2. Not going to go into too much details. The mechanism is well understood, makes total sense, very easy to demonstrate with a ball model. But what it does is it produces a whole bunch of different orientations. There's only a few that are common to both the twin and the matrix, and there's only a few which have some rational relationship. So although it's a simple mechanism for deformation, depending on which plane you're interested in, the orientation relationship between the twin and the matrix can be a little bit complex, as in those planes which are parallel can be, for instance, the 01, I can't even read that, the 1-1-1 plane, this particular 1-1-1 plane in the twin is common to the 5-1-1 plane in the matrix. But when you do have a twin, it's generally pretty obvious. You can see it in the diffraction pattern. What you see is a set of kind of double images, and you have, if we look at one systematic row of dislocation, of diffraction spots, which would be, the systematic row would be perpendicular to the twin plane. We have a mirror image of either side of this systematic row. So where does it become important? Well, it's very important to know what kind of deformation you've got, because that determines what kind of mechanisms what you're trying to decide on that are operative in a material. In the last 10 years, I guess there's been a lot more exposure to bubbles, small cavities in neutron irradiated materials at low temperatures, whether it's steels or in this particular case, Inconel X750 from the Candy reactor. Oh, actually, this isn't from the Candy reactor. This is a proton irradiation. Excuse me. This is a helium ion implantation followed by deformation. This is some work done at Queen's, and I see I've left off the reference here. I'll have to put that on reference in slide something 20. So a couple of points to note here. This band, we'll call this a band, is a twin. And within the twin, you can see some shearing of the implanted cavities. So these cavities would have been like this in the matrix prior to testing. And then during the testing, you induce some twinning, and this shears the cavities as shown. What's interesting is that the strain is seems to be a little bit higher than the 70% strain you would get from a single twinning operation. The implication is that you could have numerous twinning operations in the same volume. When this twin is tilted so that we get stronger diffraction from it, and this is a lower magnification image of that volume, you see the characteristic twinning structures. So you can't tell what it is here. You have no idea what it is because you're in absorption contrast. You're not imaging anything with diffraction contrast, but here we have diffraction contrast, and this is where the twin reflections show up very strongly along with the matrix. I mentioned about the ball model demonstration. So again, if in a live presentation, I'd be showing how all of these things come together. I'm wondering if, oh, I've just lost that. I don't know how that happened. Maybe because I'm recording this, the system doesn't like it. Oh. Oh, it's sorry. Unfortunately, that was, sorry, my fault. I shouldn't try and do an animation because it gets out of whack. I made the mistake of trying to operate one of those. It's a YouTube link to click on the link. I mentioned the ambiguity when you see these bands. Are they twins? Are they channels? Are they slip bands? If the channels are kind of, so what? It's kind of also a bulk shear like a twin, but not as regular. But if they're slip bands, so if the slip is localized so it stays on one plane, that's potentially when you could get some more intensification, more amplification of stress and failure by that means. So there have been many people who've studied lots of irradiation of irradiated material following deformation, and I would say, in looking through the many different papers, there are often cases where people describe shear bands. They can be ambiguous if they don't know, but sometimes they call them channels, which is not strictly speaking correct because it implies a dislocation channel like the one I just described. And these guys, Onchi et al., I think they realized that many years ago, back in 2003, and realized that you have to be very careful because here is a apparent dislocation channel. It looks like the loops have been swept up in this channel because there's no contrast there. But that's simply because there's no contrast, because this is a twin, and Onchi and company showed that, yeah, there's your twin. So this ambiguity is clear in this case that it's a twin. So, but be careful of reports when somebody sees that and then says, oh, well, that's a channel, because it isn't. Here's another example where there's ambiguity, but the authors left it ambiguous. Unfortunately, they seem to they do protect themselves by saying deformation bands, mainly slip bands. So basically, they can have some twins, and they're still in effect not incorrect. I'm not sure that their conclusions are going to be particularly good, because it looks like they've got a lot of twins in this particular case. really interesting thing I came across is this work on alloy A286, which contains gamma prime precipitates. It was a fatigue tested sample. On the right here, I got some examples. This is from Onshi and company, and where they're saying, look how difficult it is to distinguish between what is twin material and what is in effect a dislocation channel. I mean, that's not even straight here. So it's a very complex thing. But in this particular case, on the left here, these guys looked at this precipitate-free, apparently precipitate-free channel and called it a dislocation channel. And they came up with a very extremely hard to accept scenario where they said that the fatigue dislocations generated by fatigue are sweeping through this channel, which is created as a channel not through sweeping up loops, I'm not sure what it is, and they destroy the gamma prime. Now, the best way to interpret that is that that's a twin, and you've simply tilted the material to an orientation where the gamma prime doesn't show up. So unfortunately, people still talk in terms of channels, and this can be very confusing, can be very ambiguous. So you have to be aware of that and be careful about how you interpret what is presented. Another example here, some work by Zhao and company. They're looking at steps at grain boundaries, ostensibly produced from deformation, but I don't know where and when. No, it's very difficult sometimes to know whether features that you see in the microscope, especially if it's been irradiated, how do you know they weren't there to begin with? You know, so I would look at this, and my first reaction would be, yeah, you know, this looks really interesting and odd. This is a very odd kind of structure. There's a diffraction pattern from this area, and because of this diffraction pattern, they deduced that this was not a twin, for example. But it doesn't look like a channel either. I don't know what it is. If you look at this in a bit more detail, you've got something here. What is it? I really don't know. There is some orientation, tilt orientation, but they attributed that to slip, which makes no sense whatsoever, because slip is a planar translation. And to get slip, change in the orientation of a crystal, it has to be a subgrain boundary. The only other way is to have some constraints, but if you've got a foil, you've relaxed the constraints, it's very difficult to envisage that could be real. But you've got this peculiar structure here, which could indicate subgrain boundaries, I don't know, that in this odd shape, it could be, you could have had a different phase here, which has since disappeared. I really don't know. But channel, I'm not sure. So just to quote, they say the selective area diffraction pattern of an expanded channel. Oh, that's another oddity. They talk about this being expansion. This is kind of expanding in the direction of the arrow, which again is kind of odd. I'm not sure that is very rigorous in how that was the explanation. It certainly doesn't make, it's not too logical. And they say it's just a systemic rotation of atomic planes in the expanded channel relative to the adjacent area. It could be a twin, and we're just looking at it at a particular 1-1-0 direction, which doesn't show up the mirror symmetry. Could also be crystal where you've had two twins, in which case you go from a tilted sample back to being in register again. So if there were two twin shears, you wouldn't see them. And whatever that feature is, which doesn't look, it looks odd, and I hate to say what it is, but the rotation could also be from polygonization. If you had a string of dislocations which had all butted up against this barrier, if you call it a barrier for some reason, then you would create something that would be like a polygonized wall, and that would give you a small tilt. It's very difficult to, again, it's very ambiguous how these things get described. It seems that because this saying that there's these high stresses and deformation of the grain boundary, shear of the grain boundary, that it's the tilt of the crystal might be from pileup, but it just doesn't make sense. So what would make a little bit more sense is if you had a whole string of dislocations along a line which would be the barrier to something, in which case then you have that shear. You have that shear, and it can be explained simply by polygonization. Affect the properties. So let's think about the most common defect that one will deal with, and that's dislocations. So here's a very interesting note, schematic description of what dislocation slip is all about. If we had a crystal and we wanted to shear one part of the crystal relative to another, and so if we wanted to get from there to there, and these black points here are just there to denote a shear plane, or a plane where this part of the crystal will be in a different location for this part of the crystal. It doesn't mean that they're different atoms. It just denotes a plane in effect. So imagine we have this lattice going direct. We're looking in projection at an array, a square, a cubic array of atoms. And in principle, we could take this half of the crystal and shift it relative to this half of the crystal. But if we did all that in one action, that would be take a lot of energy, because you have to break all of the bonds, or all of the bonds here, all at the same time. And I'm going to make this pointer smaller if I can. No, I can't. Don't know how to make it smaller. We make all of the bonds, break all of the bonds. But if we break them all at once to shove one part of the crystal to the right compared to this part of the crystal, that takes a lot of energy, a lot of force, in fact, to do that all at once. So how materials actually deform is just bit by bit. So the best analogy is either a carpet. If you want to move a piece of carpet, if you had a flat carpet on a ground and you try to pull the carpet all in one movement, there's a lot of friction spread over the whole surface, and it takes a lot of force to move that carpet in one go. But what you can do is you can create a little ruffle. You can make it with the carpet, or you can make it with the caterpillar, whichever way you want. You create a little ruffle, and you only have to separate this part at any one point in time. And then you work on this part if you're weak like me, and you can only apply enough force to break one line of bonds. And then you can move one layer of atoms a little bit, and then you can move it again a little bit. So if you have a finite force available to you, you can just keep moving a little bit at a time, and eventually you go from this position to this position. So that's typically what happens in the movement. We start with the perfect crystal, we start to deform, and we go from there to there to there to there. So that's the simplest way to think of dislocation slip. Take note, this is something that might come up in your studies, you may come across it a lot. The deformation by dislocations doesn't change the arrangement of the atoms. There's no orientation change here. Ignore the fact that these are black. It's just a way to note where we have this separation of the two halves of the crystal. But these crystals, the atoms here, are the same orientation. Dislocation slip does not change the orientation of the crystal. Certainly not at the location of the slip itself. This slip operation, this change in the shape of the material, may affect the constraints, may affect elastically the whole crystal. And you may get some rotation or bending, kind of hard to say, but depends on the situation, depends what the constraints are. But there may be some effect just by simply deforming the crystal in changing the shape of the crystal in this way. There may be some effect in the impact on how this then fits into the remainder of the material. But for the atoms themselves, at the slip plane, there's no change in orientation. So there you go.